Okay, good afternoon. So let's get started today's class. So let me share my screen. Okay. Okay. So what we have been looking so far until the last class was EM, right? So and then there was this pause. I hope the pause was useful and it allowed all of you to catch up. So now we are going to study multivariate Gaussians in detail. We have already done a few things, but today we will build on those things and try to make it even more complete. And we will derive a few identities and so on. Now, yeah, so the topic of today's discussion is multivariate Gaussians. So this, yeah, so this has a lot of applications. Okay, so we are going to see several ML applications based on this, and yeah, it's a very useful topic. So see, typically whenever if you see the discussions that happen, people don't do the derivations and show you the minor details. But I am of the belief that since you are in an undergraduate program, you should be able to simplify these things yourself. Okay, so that is the reason why I'm going to spend some time doing these things by hand, and then I will expect you to also be proficient in it, so that when I ask you questions around that, you should be able to do it. Okay, ideally this topic belongs to probability, but sometimes there is no time during that course. Okay, so as a result, we will spend couple of classes on multivariate Gaussians. So then again, after we are done with this, again we will see several examples which uses this, and you will see some more EM related, and then we will go to supervised learning and all those things we will start seeing. So there will be, of course, like applications, not immediately, but it will come. All right. So the first thing we saw last class was moment generating functions. Okay, and if two distributions have the same moment generating function, then they are having the same density or same PMF. Yeah, so we saw this. We didn't prove it, but that's the idea is all the moments will be similar. So as a result, they will be having the same distribution. Okay, so for a random variable, x, right, the MGF mx of t is defined as e power export, yeah, this quantity, right? And we saw an example. If x is a normal distribution with mean 0, variance 1, so this MGF mx of t is actually e power t squared by 2. So we saw this, and then this was the first thing we saw, and then we saw an identity where we looked at moment generating function of y being some ax plus b, and the moment generating function that you get here is e power bt times moment generating function of x of at. Okay, so now if I take x to be normal, mean 0, variance 1, then we know from probability theory that this will be a normal distribution with mean b and variance a square, right? This we know. So using that identity, we can get the moment generating function for a normal distribution, general normal distribution. It will be e power bt times a square t squared by 2. So this is the two things we saw, and then we looked at multivariate normals. So multivariate normal has the density fx of x1, x2, xn, right? This is also a vector. This density is of the form 1 over 2 pi. So suppose if this is d, 1 over 2 pi d by 2 sigma to the power of the determinant of sigma to the power of half e power x minus x is a vector again, mu is a vector, x minus mu transpose sigma inverse x minus mu, right, over 1 over half, so negative. So this is the multivariate Gaussian, but yeah, this is just something that we have seen earlier, but any case, so since we are starting after some time, I'm explaining again. So when you have moment generating function for a multivariate functions, right, so that will be mx vectors, right, this will be a vector. It is given as e power t transpose x. Okay, now let us suppose that x is coming from normal, mean zero, and identity, right? So these are independent, each component is independent and identically distributed with mean 0 and variance 1. So when we have something like this, what we have is that mx of t, it becomes like t1 x1 plus t2 x2, all these terms are there, right? T transpose x is t1 x1 plus t2 x2 and so on. Each of them are independent. When they are independent, if you remember, expectation of f of x, g of x, right? This becomes expectation of f of x times expectation of g of x. Okay, so this is all that we have. So now when we do that transformation, what we will get is each component will give you a squared t1 squared by 2, sorry, t1 squared by 2. So you will get e power t1 squared by 2 from the first and e power t2 squared by 2 from the second, and all this way. So that we can concisely write as e power t transpose t by 2. So this is the moment generating function when standard normal and covariance identity. Okay, so now now if you try to generalize it to y, which is given by ax plus some mu, right? So the same identity, instead of a random variable we have a vector. So when we do this operation, the moment generating function fit, it will be a power mu t plus into e power. So here, if you remember, mx of at was there, so instead of that we will have mx of a transpose t. Okay, so that will give us e power mu transpose t. Okay, e power, or I think, yeah, mu transpose t, and then t will become a transpose t, right? So this will become t transpose. Okay, so let us write this properly. A transpose t transpose a transpose t by 2. So if you simplify this, it will become e power mu transpose t plus t transpose a. So when you take AB transpose, you get B transpose A transpose. Okay, this is an identity. So how many of you have not seen that identity? I mean, or have forgotten? Please raise your hands if you have not seen or forgotten that identity. Okay, so everybody seems to have seen. So T transpose, A transpose transpose is A, so A transpose T by 2. Okay, so this is what we get. So yeah, so we have seen this in probability class. So what is the distribution of y?
The mean is 0, but the variance is a transpose ax whole square, 8 whole square.
Okay, it is actually AAT, right? Mean is mu. Mu is a vector, so it is A times A transpose.
Yeah.
Okay. All right. So all these things we have. Okay. So now I want to do something, a new topic which is called as conditioning. So did we? I think we discussed till here, right, Siddhant, or did we discuss anything more from here?
Yeah, this was in the last lecture too. This
Yeah.
part.
Okay. So yeah. Okay. So now let us discuss something called as conditioning. So I had shared a code. So does anyone have any insight what that code is doing? Do you all remember this code? Any
Yes,
idea?
sir.
Yeah. So tell me.
Actually, like we were like transform. First, we were generating some data in standard normal,
Hmm.
standard multi-normal, and then transforming into general mu and sigma.
Okay. So let us. So first is we are drawing. So as you are saying, the first method is drawing from standard, not standard normal, right? Mean 0, mean 2 3, and variance 4339. Right. So this is I am drawing points from this distribution. Okay, Mahendra, this is what the first thing is doing, right?
Yes, sir.
So
Yes,
we
sir.
are, yeah, we are drawing points from this distribution. So looking at the figure, I have a question to all of you. So looking at the figure, is there some way to verify that this might be reasonable? Who can say what is the, how you can say that this is reasonable?
Sir, like x1 is 2 and x2 is 3. It is whole distribution centered around this point.
Yeah, so the whole thing
So
is centered around 2 3, so it is kind of
mean.
correct, yeah, as expected, right? Okay, so this is what we have. Okay, so now this matrix, as you all know, I have been telling from time again, is what is called as positive definite matrix. Positive definite matrix. And what other properties can you see looking at the matrix?
So symmetric.
Symmetric. Okay, so now if I do take this matrix and if I take its eigenvalue decomposition, okay, so what is the property that you know? Roshan, you are unmuted. Okay, so positive eigenvalues is correct because it is symmetric, it has positive eigenvalues, but besides that, can you say anything more about uh,
Sir, I think we can write it in the form of its eigenvectors and eigenvalues.
that is true. Most matrices you can write it like that. It's called
So
eigen
like
decomposition.
for symmetric matrix, we can like decompose it. Uh,
All the
like
all the
Let's
for
majors
example,
are all the majors have a positive determinant.
Yes, that
Like
is true.
if
Yeah,
it
that's a
yeah.
property of positives definite. What I'm asking is, you can take a matrix A and you can write the eigen decomposition. How do you write eigen decomposition for a matrix A? For a general matrix, if
Sir, I think X transpose BX.
huh? Sorry,
Well,
X transpose. Sorry, I just had to mute because somebody had unmuted. So yeah, tell me how you
X
can write.
transpose BX.
Okay, what is this X and B and what are all these things?
X will be the matrix of eigenvectors. Columns will be eigenvectors, and B will be like diagonal matrix with eigenvalues.
And this X will be.
Again, the same.
So
Like
what is X
columns of the
transpose?
X, columns of X will be like eigenvectors of A.
it's an orthonormal matrix.
It's an orthonormal matrix. Okay, all of you are telling a few things. So let me just try to explain this a little bit for those of you. See, everybody had linear algebra course, right? I mean, even the math department people will have, I think, right? Siddhant, you had a linear algebra course.
So actually, this is the same problem that we faced in optimization as well. The
Uh-huh.
CS students only had one linear algebra course, whereas we had three linear algebra courses. So
Okay.
some topics
Hmm.
might be known to us, might not be known to them. So
Okay, so you have three linear algebra courses, so you should answer this clearly. Okay, so what I'm asking is, you
okay,
have a matrix, right, which is known to be positive, definite, and symmetric, right? So I want to be able to write it in certain way in terms of its eigenvectors and eigenvalues. So how do we do it? How does it look? So,
Sir, it will be,
yeah, Tushar, go ahead.
sir, it will be something like QD Q inverse.
B
Where
DQ inverse. No, what is that?
yes,
B.
no sir, QD Q inverse. Yeah, yeah, that's fine.
This
Where
is the
B is
way.
the I. Yes, sir. Where B is the matrix of eigenvectors, and the D is a diagonal matrix which contains eigenvalues.
And then B inverse is what?
So B inverse is that inverse of that
B
eigenvector, sir.
transpose. B
Okay.
transpose. Basically, it is orthonormal.
So
Okay.
as it is
Okay.
orthonormal, then that will be same.
Okay, okay, okay. So many people seem to remember this, but since there are many who don't, so let me just try to explain the idea. Okay, so okay, this will take like a few some time, but let please stop me. So this is I'm mainly speaking to the CS students and MTech students, right? So have you all heard of linear transforms? Kushbu, have you heard of linear transform? Is she here?
No, so like I don't remember.
Okay. Anybody who remembers linear transforms?
Yeah, multiplying with a matrix, any matrix we multiply a matrix, we do a linear transformation.
Okay, okay. So yeah, that is correct. But the general definition is you are taking it's a function from one vector space to another vector space, right? So it is Rn to Rm in general. So that's a linear transform. Okay, and it satisfies. So basically, example. Let me give an example, right? So example is. No, before even I give the example, I should tell you what properties it satisfies. The properties it satisfies, yes, Karthik, do you remember what property should it satisfy?
Yeah, f of a transform is equal to a into f of transform, something like that.
Okay,
Sir, we can say that T of A plus B equal to T of A plus T of B,
okay, okay,
and T of alpha into A equal to alpha times T of A.
okay, good. Okay, so this so what is A and B? First of all, A and B's are vectors in Rn. Okay, so so if I let me just explain once again, so that everybody understands this this thing correctly. Okay, first of all, let me tell you, uh, for computer science students, linear algebra is extremely important. Okay, whatever you do, you have to know linear algebra well. Okay, so kind of there is a kind of a big gap here from what I'm seeing. Okay, so you have to do this, and if you have not done, you should do courses which teach you these things. See, I don't know, I mean, if you want to do anything meaningful, you have to know linear algebra. Okay, this is like the core. Okay, anyway, so let us look at some example. So let us take an example of a linear transform which takes from R2 to R2. Okay, so so what does that mean? So let us take an example. Basically what I will do is I will take numbers 4 3 3 9, this matrix, and I will multiply with whatever is the input here, right? So suppose the input is some 2 and 1. Okay, so what we will do, you know, all of you know the matrix multiplication. So can you tell me what is the answer here? 11 15, right? Okay, so now let us do one more. 4339 times shall I just do one thing? I will multiply this by like 3. Okay, so this is 3 into 2, 3 into 1. Yeah, so what is this?
3345.
3345. Okay, so what you can see, this 3345 is actually 3 times 1115. So which property have you checked? Second one. Yeah, so this is second property. All right, so now let us check a first property. We will check with some example. So 4339, let us say I will take with 1 2. So what is that?
10, 21.
10, 10, 21. Okay, so now in order to check the first property, what will I do? 4, 3, 3, 9, and what I should do? 2, 1 plus 1, 2, right? So what is this?
2136.
21, 36. Okay. So can you see that we have, it is actually the sum of this and this, right? Sum of this and this. Can you all see we have verified property 1?
Yes, sir.
Yes, sir.
Okay, so this is done. So basically what we are showing is that every linear transform, sorry, every matrix is a linear transform. Rishabh, you have something to say? Okay.
No, sir.
Okay. So every matrix is a linear transform. Okay. Does everybody see that? You take any multiplication by a matrix, it's a linear transform. Are there any questions so far?
No, sir.
Okay. So now the reverse question. So this is for the math department. So is every linear transform, okay, is every linear transform like similar to matrix multiplication? See, you understood the idea, right? So every multiplication I could show that it is a linear transform. I am asking, take a linear transform, is it same as matrix multiplication? Siddhant, what do you think?
It's more than
yes,
this.
Sorry?
actually, there is some equivalence like between transformation and matrix multiplication.
Okay,
They
there is
are
an equivalence. Yeah, so they are equivalent. So tell me why. So if I give you I
so
will
there
say,
was proof, we had proved this in our linear algebra course, but in a not multivariate course, I guess.
okay, so is it something only you guys did, or is did CS students also do this?
No, no, sir. It was only math department.
Okay. So let me give you a proof if nobody remembers. So let us take a linear transform T, right? Now, okay, so the first thing we must understand is that every vector can be represented, every vector is represented in terms of the basis, right? So what that means is, so you have coordinate axis like this. So this is a vector in R2, right? So this vector has coordinates x comma y. What is the understanding is that you are moving x units here in the x axis, okay, and you are moving y units here, right? So that is how you get x comma y. So basically in the x axis there is a basis which is this vector, unit vector, which we call it as E1, and there is a basis E2 like this. Okay, so whenever I write AB, the idea is I am taking A times E1, the vector E1, and then I am doing B times E2. So that is the understanding of x comma y. Okay, so now, so that idea I hope is okay. So now, so whenever you have you have been given a linear transform T, you can always ask what is T of E1. Okay, suppose T of E1 is equal to alpha 1, alpha 2. So what is the meaning of this? I mean, I have already told you, right? This is nothing but alpha 1 E1 plus alpha 2 E2, correct? And I can ask what is T of E2 as well. Suppose T of E2 is beta 1, beta 2. My matrix equivalent for this T is alpha 1, alpha 2, beta 1, beta 2. So let us check if that is indeed the case. Suppose I try to do a linear transform T on a vector A, B. Okay, so what is the equivalent of this? So this is nothing but T times A E1 plus B E2. Okay, so that is nothing but A times T E1 plus B times T E2. Okay, that is nothing but TE1 is this, right? So I will get A alpha 1, A alpha 1, A alpha 2 plus B beta 1 plus B beta 2. Okay, so now let's multiply with this matrix and verify whether that gives us the same answer. So this is one side. Let me write here alpha 1 alpha 2 beta 1 beta 2 AB. If I multiply, do I get the same thing? Yes? No?
Yes, sir.
So Mahendra, did you see some proof like this?
Yes, sir, but we proved in general, like.
Okay. Yeah, so general
similar to this, yeah.
Yeah,
It was similar to this.
general is fine, but you should remember the particular when it comes to usage, right? So that is the
Yes,
point.
sir.
All right. So forget about this now. Everybody understands this. CS students, is it clear? MTech students.
Yes, sir.
Yes, sir.
Yes.
Okay.
Yes,
So
sir.
this is the idea. So what is the idea is that linear transform and matrix multiplication are one and the same. Okay. So that is the reason when you, so why the matrix multiplication first of all is so complex. Like if you take two vectors, right? So if I take two T1 and T1 is a linear transform, suppose T2 is a linear transform, and if I compose it, right? So that is how you get matrix multiplication. It's like multiplying the matrices corresponding to each of this. So this is like multiplying MT1 times MT2. Okay, so this is any vector x. So that's why you have matrix multiplication, which is that like this, and all this you multiply, right? Anyway, so the point of all this is not yet achieved. So what I am trying to say is a little more involved. So let me explain a little more. Okay, so far it's fine. So this is just a background on matrices and how you are able to do. Okay, so what is it that we were trying to do? We wanted to write sigma in terms of some combination, right? So that is where we were. So sigma is a symmetric matrix. Okay, symmetric matrix. So yeah, so there are a few things that you must know for a symmetric matrix. So one of the things is it is diagonalizable. Okay. So again, this proof you would have seen sometime, but anyway, without proof I will state this. So what that means is sigma can be written as PDP inverse. Okay, this is one thing, and then there is also diagonalizable, and there is another property that P inverse is same as P transpose. Okay, so what you can get is that sigma is equal to PDP transpose. Okay, so where P is the eigenvectors and D is the corresponding eigenvalues, and P transpose is the transpose of that matrix. So let me show you these computations. I think that will be useful. Okay, so coming over here, so what you can do is you can get eigenvalues and eigenvectors by multiplying them. Okay, so this is the sigma matrix. You can get eigenvalues and eigenvector decomposition. Now let me just for the benefit of doing this, let me print sigma, and let me print what is it that I need to print? Eigenvector multiplied. This is the shortcut for multiplying eigenvalue times I of 2 times np dot transpose of eigenvector. So this whole thing I will call it sigma 2. Okay, and then I will say print sigma 2. So I guess it takes a little while, but what it is saying, NP not defined. Okay, I have to start from top. Okay, so can you all see this? So I have reconstructed sigma by doing PDP transpose, right? So eigenvector is the matrices of all the eigenvalues is the eigenvector matrix, and the transpose is P transpose. The inner guy is the diagonal entries which are written along the diagonal. I am not understanding if people are following this discussion.
Yes, sir, it is clear.
Yes, sir.
Yes, sir.
Okay, so
Yes, sir.
okay, so we have sigma is equal to PDP transpose. Okay, so why did we do all this complicated calculations? Can someone make the guess? Somebody is unmuted, so Siddhant, you are unmuted. You want to say something?
Oh, sorry.
Yeah. So we have this sigma is equal to PDP transpose. What is the idea? So basically, what we can do. I mean, it's very difficult to tell what is the idea. But so suppose you have a diagonal entries which is 2 0. So let's say 4009. Okay. I can take the square root of a matrix. Okay, if the diagonal values are positive, I can take the square root of matrix and I can call it d power half, which is nothing but 2003. Why is that true? Because if I multiply d power half with again d power half, I will get the original matrix. Okay. So because if I multiply with this again, I will get the original matrix. You can check it. Okay, so what we can do is we can write this as P times d power half, okay, times d power half P transpose. Okay, I can do this decomposition. Now what I will do is I will write this as P d power half. So d, what is d transpose? If I take d transpose, what do I get?
Equal to D.
It is equal to d, right? So basically I can write this as d power half transpose P transpose, right? So, and I have already told you AB transpose is equal to B transpose A transpose, right? This we have, yeah, so this becomes P d power half times P d power half transpose. Okay, so what I am saying with all this incredible amount of calculation is that you have, if you come back, right, if you have y is equal to ax plus mu, your A can be chosen in this manner. Okay, because AA transpose is going to give me sigma, I can choose this equal to A and this will be A transpose. So what I can do is I can generate Y by doing A Z plus mu, where A is this matrix PD transpose, PD power half, right? So where A is equal to PD power half. Okay.
Sir, can you repeat the last part? As in, I got that we did A transpose.
Yeah,
After
so you
that,
got
Y
this.
equal to AZ.
Yeah, y is equal to
we
AZ.
make a
Yeah,
norm.
so now Z is a multi-normal. So Siddhant, please help me. So normal and identity we have Z. Okay. So if I do AZ plus mu, what is the distribution of Y?
Okay. Oh, so mu, the new mean is mu, and it is A square I. A
No,
square.
no.
No need to add I.
No, A transpose, right? A
Oh,
square,
yeah.
yeah. But A transpose is what is sigma, but A transpose I have shown it to be equal to sigma. So this is equal to normal mu and variance sigma, right?
Yes, sir.
So basically by taking, normal zero identity, I'm able to get the desired distribution that I wanted. Okay, does that make sense?
Yes, sir.
Okay. How about the others? Are you all understanding so far? Can I just quickly do a chat? Okay. Okay, all the, yes, a few of master students have also responded. Okay, so this is one. See, I'm not just doing for time pass. Okay, believe me, I have tried to cut as many portions as possible, but I need to teach you a few things which require you to be properly well versed in this subject. Okay, so anyway, so this is what it is. Now I will show you another way to get this particular matrix. Okay, so what is that matrix? Where are we? 4339. Okay, so suppose I tell you 4339 I can get by multiplying let's say small p0 qr. Okay, suppose I tell you that you can get p by multiplying this. Okay, so if I tell you that if I multiply these two matrices I will get this, then again if that PQR exists, that also will give me the same decomposition. Does everybody understand this? Suppose this is true, right? Then A equal to P0QR also works. Yes, also works in this, because mu anyway will be separately added. So when I multiply A times A transpose, this is nothing but A transpose. When I multiply, if I get 4339, which is same as sigma, I am done, right? So this way we can also do. Okay, why we are doing it, I will you will soon see, but let's try to continue doing this. So how do we solve for this? So let's try to solve for PQR. So what is the value? So yes,
P equal plus minus 2.
yeah. So P is equal to P squared is equal to 4. So let us take P is equal to 2. Okay.
And PQ equal to 3.
PQ equal to 3. So therefore Q is equal to 1.5. Okay, or 3 by 2. Okay.
And
And
Q
then
square plus R. Q square plus R square equal to 9.
Is equal to 9. This implies R is equal to under root square root 9 minus 9 by 4, right? So what does this simplify? R is equal to under root 27 by 4. Okay, so what I have got now, a matrix of this form: 2 0 3 by 2 27 by 4. Okay,
So just write it. Sorry, sir. Nothing.
Yeah, so that's what we will do. Okay, I don't know why I 20 square. Yeah, this should be. If I have done the calculations correct, when I did the calculations here, it was not correct. But anyway, so let me put this as 27 over 2. So
27 by 4.
27 over 4. Yeah, 27 over 4. Okay. So again, is it the same? I don't know. It doesn't look like the same, right? Let us verify whether A2 into A2 is actually sigma. .75. So some mistake I have done. Somebody has to tell me what mistake I have done. So if I multiply, what do I get? I will get P squared.
Sir, I think the sigma we have chosen is
not this, is it? Sigma is different. 4339. No, 4339 is what it is, right?
Yes, I'm sorry, sir.
Yeah. P squared PQ, that is correct. Then PQ, that is also correct. and q squared plus r squared. Q squared plus r squared is equal to 9, and so pq 3 by 2, then 9 minus 9 by 4.
So while checking, you multiplied A2 into A2 only, right? Over there. In the
Yes, yes,
which
yes, yes.
transpose.
Transpose.
Yeah.
Very good. Okay, 433 now. All right, so it does look similar now for whatever reason. It did look similar much when I ran before, but yeah. Okay, so why did we do this complicated way of doing things, right? So what is the purpose of decomposing it something in this manner? So let's try to understand that. Okay. So are you all understanding whatever I have discussed so far?
Yes, sir.
Okay.
Yes, sir.
Okay. So now let us take an example of a bivariate density. Okay. So let's take a bivariate normal distribution. Uh, so if you remember, for a bivariate normal distribution, if I write the covariance matrix, okay, so what will this entry be? So this sigma I am trying to write for bivariate.
So covariance of x1 and x1.
Yeah, so covariance, yeah, that will be variance. So that will be sigma 1
Sorry,
squared.
variance.
Yeah, so that is correct. Covariance of x1 comma x1 is nothing but variance of x1.
Yes.
Okay, so that is correct. So sigma 1, this is sigma 2 square. This entry will be rho times sigma 1 sigma 2. This will be rho times sigma 1 sigma 2, where rho is called as what is that? Not covariance, but something else, correlation. Okay, so this is equal to covariance of x1 x2 divided by standard deviation of x1 or square root of variance of x1 times square root of variance of x2. Okay, so we can write something like this decomposition. Okay, so somebody is unmuted.
Have you seen these shows?
Okay, so this is what we have now. What is the benefit of doing this? So let me try to explain that. So now suppose this sigma I was able to get by this x comma y. I got it as equal to sum p0 qr times z1 z2 plus mu1 mu2. Okay, I have got this where let me emphasize, where p0 qr times p0 qr, okay, gives me this is equal to sigma 1 square sigma 2 square. Okay, so now let us have this, and now so far I hope everything is fine. So now what I am interested in is conditional distribution of y given x is equal to some small value x. Okay, that is what I am interested in. I want to know the conditional distribution of y given x is equal to small x. This is my goal. Okay, so again conditional distribution comes everywhere in many topics. Okay, so it comes in Gaussian process, which I am planning to do, Kalman filters, and linear dynamical systems. Several machine learning algorithms uses conditioning. Okay, so now let's try to understand how we can get this distribution, right? So what essentially we have is that x is equal to pz1 plus mu1, y is equal to qz1, not rho z1, qz1 plus rz2 plus mu2. This is all the things that we have. Okay, now when x is equal to some small x, okay, so what is the value of z1 when x is equal to small x? Yes, what is the value of z1?
x minus mu1 by
x minus mu1 by p.
Yeah, x minus mu1 by p. Okay. So this is what we have as z1. And what about y? So y we can write it as, yes, so you can write it as q times x minus mu1 by p, right? Because z1 is this, plus r times z2, okay, plus mu2. Okay. Does everybody understand these steps? Siddhant?
Yes, sir.
Okay, so what is the thing that is random here? So by the way, this is small x. Huh? Small x is a value that capital X has realized. Okay, so what is the thing that is a source of randomness here?
Z2.
Sorry?
Z2.
Z2. Yeah, this is the only source of randomness. So can someone tell me what is the distribution of y given x is equal to small x, what it will be?
The mu2 plus this q x minus mu1 by p.
Yeah, so this will be mu2 plus q times x minus mu1 by p. Very good. And what is the variance?
R square.
R square. Okay, very good. Okay, so this is what it is. So now all we need to do is we need to solve for q, p and r square in terms of these parameters. So that is all that is left. Okay, so we can solve for that very easily. So p is equal to, now let us try to put p. So p squared is equal to sigma 1 squared, right? So this is the same thing Mahendra helped me calculate that time, right? So what was that? So p squared is same as sigma 1 squared, therefore p is equal to sigma 1 I will take. I can take minus sigma 1 also, there is no problem, but let me take just 1. Then what else? PQ is equal to rho sigma 1 sigma 2, therefore this implies Q is equal to rho sigma 2. Okay. Then what about the last one? Can someone tell me what is R square? So R square is equal to
sigma 2 square.
Sigma 2 square minus p square.
Minus p.
Right?
Minus q square.
Minus q square.
Yeah, so minus q squared. So that will be equal to sigma 2 squared times q squared is this squared. So sigma 2 squared 1 minus rho. Okay. So putting all these things.
So 1 minus rho square.
1 minus rho squared. Okay, thanks. So this will be normal distribution with mean mu 2 plus this is rho sigma 2 by sigma 1. So that becomes rho by sigma 1 x minus mu 1. Okay, and r square is this. Okay, so this is how we can get conditional distribution easily. I don't know whether it was easy, but I feel that this is easy. What do you all feel? Siddhant, yeah.
Yeah, so sir, I just want to confirm the whole efforts that we did for that P0QR format, that particular form. Was so to solve this that z equal to ax plus mu sort of a thing that it comes in this particular format.
Yeah, it comes in this format. Then you can put that back into the y equation and get the distribution of y in terms of the only randomness left, which is z2.
So had it been in any other form, then apart from z2, there would have been any other factors too involved.
Yeah, that we couldn't have done. See, if it was some other term was there, some PQ t times z2, I wouldn't have been able to solve for z1 and z2, right?
Alright, because so we only wanted one random variable.
Yeah, we only wanted one random variable. See, I can ask you to just take the words for granted, but it is satisfying to see these expressions, right? So now we will do it for a more general case, okay? And then we will use, once we have derived it once in the class, then later on whenever I invoke that, you will not have any jitters. It will feel convincing, okay? So Siddhant, any other questions you have?
sir.
Okay. All right. So, is there any? So let me just first of all check if this is indeed conditional distribution. So let us see conditional Gaussian distribution. So let us just check. I mean, I just derived it right now, right? So. Yeah, so you can all see. So let me copy this term. So if you haven't got, there is some mistake that I have done, but if you have got, then well and good. So looks like what are all the terms I am missing? I am missing. Okay, so can someone help me fix this?
Yes, actually, sir, there is a row of sigma 2 by sigma 1.
Yeah, it should be rho sigma 2 by sigma 1 in the mean part.
In mean part, yeah.
Here, okay, Q by P. Q is this one. Okay,
Rho
Q
sigma
is
2.
yeah, rho sigma 2, and P is
Sigma
1. Oh, okay. So that is correct. So there is a sigma 2 that I have conveniently ignored, and the other one seems to be there. But why did I get sigma 2 squared? It says it should be sigma
Sir, it
1.
is x1 given x2 equal to a. We have calculated for x2 given x1.
Okay. Fine. So they have done for x1 given x2 is equal to a. We have done x2 given x1 equal to a. So that is the reason that this 1 and 2 are interchanged, right? Okay. So this is the idea. Okay. So when you are taking multivariate, so this for bivariate I showed you the benefit of trying to decompose in this manner. Okay. So in the next class we will try to see what is the benefit of doing for multivariate when I decompose in this form, how do I decompose in this form, and then try to get multivariate densities. Okay, that is something for the next class, which is when we do that we will get these matrices. Okay, so this is for next class we will do this, that is tomorrow at 12 o'clock. Okay, so let's just stop here and I will continue tomorrow. Okay, so if you have any questions you can stay back. In particular, if you have some questions related to linear algebra and all which you want to ask, that is also fine. I can spend some time. All right, otherwise we will stop here. So thanks.
Sir, LU decomposition is possible for any matrix, right?
LU decomposition is possible for any matrix, that is true.